Good morning. This is February 17, Monday. Um, Perspectives on Data Science, Lecture 10, Linear Regression Part 1. So in this deck of slides, we are going to see what is linear regression. So it's the basic stuff. So we have dedicated 2 lectures to linear regression. So we are going to discuss Part 1 now and Part 2 on Wednesday again. So regression versus classification. So the name itself says regression is something like a line, or it tries to predict the future values. Classification is to classify things. So for example, if in the data set we have male and female, we'll try to classify based on the other input values. So that's something classification. And regression is something to predict. So regression algorithm predict a continuous value based on input variables. And regression is something straight line. So we discussed earlier, straight lines are for continuous variables. So classification is something discrete. So if we take, for example, a data set with a male and female, and if we have like 60 males and 40 females in the data set, so if we plot what we say, if we plot a bar chart between the number of gender and the type of gender, there will be bar charts with discrete values. So this is a discrete data set. Okay. So the discrete data sets are used for classification, and the continuous data sets are used for the regression. What is the temperature going on to be tomorrow? So that's prediction. Classification, identifying which of the set of categories and observation belong to. So that's something classification. So will be cold or hot tomorrow. So that's good example. Both the examples are the same thing based on weather. So what's the weather to tomorrow? That's the prediction. And whether it's going to be hot or cold, that's classification. So that's the basic difference between regression and classification tasks. Even I'm seeing these slides now, so I'm not sure which is going to come in the next slide. So what are linear models? In statistics, a linear model is one that assumes linearity, often seen as synonyms with linear regression model. Generalized linear models also include logistic, Poisson, Bayesian, etc., PCL, time series models. Think of linear as reducing the complexity of a model by assuming there is an infinite line that adequately models reality. In statistics, a linear model is something that assumes linearity. It's something, if you know what is y equal to mx plus c or y equal to ax plus b, so you are good with this slide. So that's the linearity curve. So mx plus c, that gives the angle between the angle from the origin and the straight line. So that's something linearity. So the regression deals with the linearity, the straight line. So we have different types of linear regression. So simple linear regression and multiple linear regression. If our model is trying to predict one output based on one input, that's simple linear regression. And if our model is trying to predict one output based on multiple inputs, so that's multiple linear regression. So for example, if you are going to, so that's the second classification. But for example, if we look at if we try to understand single input and multiple inputs, for example, if we are trying to predict if a person will get an admission in the university based on his GRE score. So that's one score we are trying as the input, and we are predicting if he gets the admission or not. So based on one input, we are trying to predict the output. So that's called simple linear regression. And coming to multiple linear regressions, for example, if we are trying to predict if a person gets the admission based on his age, based on his scores in his undergraduate, and based on his GRE. So we are considering multiple inputs. So that's we are trying to predict one output considering multiple inputs. So this is called multiple linear regression. Okay. Any questions on simple and multiple linear regressions? So we'll try to read what's here. Linear regression is one of the most commonly used techniques in statistics because most of the data are uh, linear in real-time data. Uh, yeah, that's real. It's linear. So linear regression is one of the most common techniques we'll use in day-to-day life. It is used to quantify the relationship between one or more predictor variables and a response variable. Yes, simple linear regression quantify relationships between one predictor variable and one response variable. Response variable in our case, if we get an admission or not. Predictor variable is GRE score. Okay, so that's we're trying to predict one response variable using one predictor variable for simple linear regression. For multiple linear regression, we're trying to predict one predictor variable with more than one. I mean, we are trying to predict one response variable with more than one predictor variables. So that's the difference. Next. Questions regression analysis answers. The major area. Causal analysis, forecasting effects, trending forecasting. Causal analysis asks the question, is there a relationship? So that's causal analysis. For example, in business, I'm going to read through these slides. So if you have any questions, you can ask me because it's clearly written everything out here. So is there a relationship between advertising spending and revenue? So that's something we can ask in business. So we are asking about the relationship. And in medicines, we're asking, does the drug dosage affect BP of patients? Does the body weight have an influence on the blood cholesterol level? So this is the relationship. So this is called causal analysis. Agriculture, how do fertilizers and water change crop yields? So this is multiple inputs and one output. So this is multiple linear regression example. And psychology is anxiety influenced by personality traits? It could be multiple, what's that we say? Multiple linear regression or single linear regression based on the number of traits in the problem. Biology, does changing oxygen level in water simulate plant growth? Next, forecasting effects. We have discussed a lot of examples for forecasting, I guess. Whether how is the weather tomorrow? That's it. That's a forecast. Right? Medicine, with X cigarette smoke per day, why hours of sport, the life expectancy in Z years. In biology, how much will 5 additional weeks of sunshine and 100 mm of rain change the percentage sugar concentrated in wine grapes? So these are some of the questions for forecasting effects. And if we come to predicting trends in data, we'll ask the questions, as we change the independent variables, how much does the dependent variable change? So this is the prediction trends. So rate of change in input, how is it affecting, I mean, how the output is affecting with the rate of change in the input. So this is called predicting trends in data. So medicine, by how much does the life expectancy decrease for every pack of cigarettes smoked? So this is the problem statement for predicting trends in data. So any questions on these three categories: causal analysis, forecasting effects, and predicting trends? Linear regression pros: simple model because it's just one equation. There is nothing more mathematically complicated. It's equation y equal to mx plus c. So it's simple. So that's one pro. Simple model. The linear regression model is the simplest equation that can express the relationship between the multiple predictor variables and predicted variables. So how is that equation going to change for multiple inputs? We are going to see that. Computationally efficient. Yes, it's easy to compute because it's just a linear regression. So the computer don't take much computational power to do this task. The modeling speed of linear regression is fast as it does not require complicated calculations. Thus, it can run predictions quickly. The amount of data is large. So interpretability of the output. The ability of linear regression to determine the relative influence is one or more predictor variable to the predicted value is one of the key reasons for the popularity of linear regression. So for the data we have, it tries to make a single line uh, with the less errors. And if we are trying to predict the x values in the future, so the same straight line that's going to be in the future, and we are going to see where the point is, and that's the prediction we get. So it's simple. It just takes y equal to mx plus c equation and it tries to extend the line, and it gives what's the output in the future. Linear regression cons: oversimplistic. It's too much simple. It's too simple. Linearly assumptions. So this applies to only linear data. So if our data has something like parabola, some curves in it, so a simple linear line can't predict more accurately. So that's one problem with linear assumptions. And independence of variables, assuming that the predictor variable are not correlated with each other. This is rarely true. So, for example, we need to check the multicollinearity in our models. I guess you are aware of multicollinearity. So, if two of the predictors are more having more correlation with each other, so that's called multicollinearity. So, linear regression doesn't deal with multicollinearity. So, it always assumes that each of the input is independent to each other in the predictions. So, there are some models which will take the relationship between two predictors and will try to give the hyperparameters like weight. But linear regression always assumes that each the independent variables are independent to each other. That may not be true. There might be some relationship between the x variables as well. So here x variables, independent variables, everything is same. Y is dependent. A predictor variable, predicting variables. So everything is same. It's just the English terms. So variables in regression. The regression framework is characterized by the following: dependent variable and independent variable. Simple. Y is the dependent variable and x are the independent variables. So y depends on x. So we are predicting y with the usage of x values. So x is the independent variables and y is the dependent variables. So dependent or response variable is a variable that we are interested in and want to model, such as sales of particular product or a stock price of the publicly traded firm. Explanatory or independent variables, set of variables that we think might be useful in predicting the response variable. So that's the same thing we discussed now. In an experiment, the researcher is looking for a possible effects on the dependent variable that might be causing by the change in independent variables. So that's an example. Response variable versus predicting variable. Response variable is a random variable. It varies the changes in the predictor along with the other random changes. Predicting variable is a fixed variable. It does not change with the response, but is set fixed before the response is measured. So response variables are x variables. It varies the changes in the predictor with other random changes. So if we try to input more x values, so each of these may have less dependency on y variables. So x variables are independent to each other, but the model may think if we add more, so it will make the changes in the hyperparameters as well. So here is the difference: response versus predicting variables. Effect of different cholesterol medications on human LDL levels. Response variables is change in LDL levels. Predictor variables is type of medication. Simple. So here miles per gallon, it's predicting average driving speed and acceleration. So relationship between driving habits and fuel efficiency. So these are the examples which you can see in order to understand more about response and predicting variable. It's simple. We are predicting y, so that's response variable, and whatever we are trying to predict using x variables, so those are called predicting variables. That's it. And here, to analysis study association of continuously measured variables. So here, if we go in this plot, so linear regression is not useful to make better predictions in this case because the points are distributed widely. So we can't make a single line without more errors. So linear regression is not something that will be useful for this data set. We need to go to the other models, other model building parts to predict these values. So linear regression is only useful if your data was in a straight line. So here you can see Here you can see all the data points are scattered in a straight line, whether it's positively or negatively. I mean, in this way or this way. So this is called positive correlation, and this is called negative correlation because the line is coming down. Okay, so this is positive and this is negative correlation. Both are strongly correlated because all the points are scattered together. So this is strongly correlation, but this is positive and this is negative. It's not something like negative correlation is not something, it's not correlated. It's also correlated, but in the other direction. That's it. Both are the same. Just the sign, you can say this is plus and this is minus. That's it. So correlation analysis concerned with measuring the strength and direction of the association between variables, and linear regression predicting the values of one variables given the values of the other variables. That's it. General model, simple linear regression, simple and multiple linear regression. Again, one, if we have one input, that's called simple. If we have multiple inputs, that's called multiple linear regression. So since we have one input, that's one x, we have multiple inputs, x1 and x2. So this is the equation. It's again a simple straight line, so there won't be any powers. But for example, if this is the case, we just can't use a straight line to predict. So we need to use some type of hyperbola, some curve to predict this. And for this terms, we use x squares. So since we are dealing with linear regression now, we are it's not our problem now to concentrate on this one. But linear regression is a straight line. If you have one input, this is the equation. If you have multiple inputs, then we have multiple weights. So beta 1, beta 2 are called weights. So these weights will be assigned based on the hyperparameter we give. So we try to make good weights using the hyperparameters. That's the use of hyperparameters here. General model. So this is the general model scatter plot. So simple linear regression. Okay, he's zooming it. So zooming in every, we have discussed everything. Model flexibility, main effects and interactions. So first order model. Model 1 is the most straightforward generalization of simple linear regression. It states that for a fixed value of either variable, the expected value of y is the linear function of other variables, and the expected changes in y for the unit increase in x1, x2, and b1, b2 independent of the levels of x2 respectively. So this is something first order model. Let's see how it. So this is the first order model. If you see the graphs, you will be more easy to understand. Yes. So this is the first order model. This is the second order model. This is the first order interaction model. This is the second order interaction model. Simple. So you see the lines here, everything aligned parallelly. But if you go to second order, first order interaction model, there are some lines which are going in other directions. So for example, these are the inputs. So not every input has the equal weights. We'll change the weights of the inputs again in positive manner and in negative manner as well, depending on the correlation. So this is the first order interactive, second order and second order interactive, and the equations here. Type of linear regression, simple, multiple we have discussed. We also have logistic regression. So that's called S curve. So it tries to predict 0 or 1. So the basic usage of logistic regression. Ordinal regression, one dependent variable, one independent variable. And multinomial regression, one dependent variable and one plus independent variables. Here also one plus independent variables. Discriminant analysis, one dependent and one plus independent variables. So our interest is to see simple and multiple linear regression models in this lecture. We are going to discuss each and everything in the later lectures. So multiple linear regression objectives. Simple, it's again repeating the same thing. Prediction, response variable, modeling the relation between the response variable and the explanatory variables, testing hypothesis of association relationships. Linear regression, the basis of what we will be talking about most of the class is the linear model. Virtually all other models for studying dependencies among variables or variations on the idea of linear regression. All models are wrong, but some are useful. The George gave this statement. John gave, embrace your data, not your models. Okay? So the models are doing good, but your data is not doing good. So that's what the John is saying. So try to get your data more accurately before you try to predict instead of tweaking models. That's not true nowadays, I guess, because there is a lot of research going on in the medical field where we need to tweak our models to perfect the classification tasks. Multiple linear regression models. Again, this is the equation we discussed. So these are the assumptions. So the data is linear. So that's our assumption, which is not real. I mean, which is not true in real world, but our assumptions are these: linearity. So the data has linearity, consistent variance assumptions, um, independence assumptions. So we'll say constant variance assumptions. So we constant variance. These are our assumptions, and we assume that the input variables are independent to each other. Independence assumptions. So later we assume normal. The model parameters beta naught, beta 1. So unknown regardless how much data are observed, estimated given the model assumptions, estimated based on the data. So in the equation, we know x1, x2, and so on. We do not know what are beta and what is epsilon here. So we will try to predict the values of these using the model we build. So for that, first we assume this, and then we'll tweak our parameters to fit our model. Okay. Multiple linear regressions, model in matrix form. So these are the inputs, this is the output, error, and coefficients. Y equal to x beta plus epsilon. Parameter estimations, the same thing. So we are making this term as this one, we're inverting it. So that's the same equation. So different forms to write the equation. You can go through this thing. These are the formulas to calculate the residuals. So what are residuals now? So we are trying to predict something. So for example, we have trained our data set and we are testing it. So we are testing, that means we are trying to predict it, right, in the testing data set. So we have the labels and we are trying to predict those labels. For example, if our label uh, and the predictor label is different, so the distance between the predicted variable and the actual, I mean predicted value and the actual value is called the residual. So how do we calculate that? So we'll just subtract the distance between these two. So this is the error, this is the actual, this is the predicted. So we need to know the distance between these two. So that's the formula right there. So the predicted minus actual will give us the distance between these two. So that's the error. So this is how we calculate residuals, and this is the formula. Again, if you understand the concept, then you can easily form the equations. So mean squared error, we'll just take out all the errors. We'll just summation of that. We'll first square that because there might be some negative values as well. So distance negative means the other direction. It's not like no distance, right? So we'll just square that and we'll just square root that to get the mean square errors. So what does that mean? So we are trying to calculate the average error in the prediction values. So that's the mean square errors, and that's the formula. Parameter estimations, chi-square distribution, assumptions, simple. Model interpretation, beta naught, beta I. So that's the weights we say. The response variable, and we're trying to predict this variable using these variables. So that's an example. You can go through. We have given almost a good amount of examples. This is the output screenshot. Okay. So this is the data set we are considering this example. We have state, SAT, income, years, public, and so on. And we're saying it do not have any null values, and this is the data type. So this is something similar to your homework, I guess. We are seeing the data types and the head, and this is the correlation matrix. You can see every variable is 100% correlated with that variable, obviously, because both have the same values. You can see the correlations here. The higher the number, the better the correlation. Just give me like 4 minutes, 3 to 4 minutes, we'll finish it. Yeah. So this is the correlation gain. So this is the output, how it looks. So this is the value we have tried to predict, and we used these two inputs, and we tried to find its coefficient, standard error, t, p-value, and everything. I think you know about these, or if possible, we'll discuss it in the next lecture as well. So this is some useful stuff to predict. If you have your x values, you can predict your y values using these equations. You can form the equations taking these numbers. So the beta values, coefficients, beta naught and beta 1. Let's see how that is. So beta 1 and beta 2, beta 3, beta 4. We have just predicted it. These are the coefficients. Coefficients are beta values. Standard errors, you can see the errors, p values. So how significant is that variable in predicting the y variable? Okay. If it's like less than 0.05, we'll say it's more significant. So it's significant at 95% interval time. Okay, let's just wrap it up. Multiple simple versus multiple marginal, causality versus association, SAT. If possible, we'll try to go through these last few slides in the next lecture, or else you can just go through it's everything we have discussed till now. So that's the end of lectures. Any questions? Homework? Oh, what's the homework on? Uh-huh. Oh, I'm not aware of the homework. If you could mail, I'll just try to see what's with the homework. I'm not sure what the homework is. Any more questions? And time for quiz. Let me stop sharing the screen. If you are in a hurry, just try to mark anything. That's fine. That's just for attendance. Since we do not have time, we haven't thought of much into quiz. So this is the code for quiz.